Okay, so today's stuff. It's picking up the pieces from where I left off. There was one thing that I covered that I did not do a particularly good job on, and I went back and came up with a different formulation for it, and then we're going to explore even deeper into something else. All right, so we're still in the situation where we're talking about energy and how energy is the coupling of some potential to some object. So for example, you have an electric potential that looks like this, and I always draw it wiggly like that just because that's the arbitrary shape that I choose. So this could be an electric potential, and then a charge attaches to that, or a charge interacts with that at some location. So it will be some position here. This is going to be the potential up here, and I probably shouldn't use V. I should probably use U, but I forgot that I was going to switch the notation a little bit because we're going to have a lowercase v a little bit later when we talk about velocities. Anyways, this is, you have some charge, it couples to that field, and it has some potential that's given by the charge times the height. This is the height. The same thing happens with the gravitational potential. For example, you have, what is it, G? H is the gravitational potential, where H is the height, and then you couple it with the mass, and so mgh is the energy you get in the gravitational field. In this case, gh is replaced by the potential, if it's an electric potential, and then you have Q is the charge that couples to it, and QV is the energy that you get. So this is the energy, the potential energy that you get from gravity. This is the potential energy you get from a charged particle, an electrically charged particle in a voltage, or some other particle that has some other charge in some other potential, with a generalized potential V and a generalized charge Q. Okay, so along with this, any individual particle can have a number of quantum properties, a number of different charges, and so it can interact with a variety of different ambient fields. So you might have a gravitational field, so this mgh, so like here's your gravitational field that looks like this, and it's going to have some mass that's going to couple to that gravitational field, so this, and it might have the strong nuclear force that's going to have a different shape. So all these potentials, they exist at every point in space, right? And whether you interact with them or not depends upon if you have a charge that couples you to that field or not. And the strength of that interaction, or the energy that you get from that interaction, is contributes to your potential energy. So just a reminder that there are two types of energy that you can have. One of them is energy because of position, and one of them is the energy you can have because of your motion, velocity. Okay, and so these are potential energies, and this is your kinetic energy. And there are different kinds of kinetic energy that you can have. For example, you can have kinetic energy in any of the three directions that we live in. If we lived in a four-dimensional space-time, or we do live in a four-dimensional space-time. If we lived in a four-spatial dimension space-time, then you would have an additional kinetic energy that you can have in that direction. You can also have rotations. So here's an object that's rotating. That motion can be broken down into individual chunks of this that are moving around. Either way, you can kind of describe those velocities and formulate it into some kind of kinetic energy. Kinetic energy is also going to have some function associated with it. So for example, for the case of, it's like you could imagine a potential in velocity space. So this is a potential in position space where you have mgh or something like that, or you could have 1/2 kx squared. So that's like the spring force, or the spring energy. Energy from a spring is 1/2 kx squared. So this, again, is a function of the position. So when you compress the spring, that's some location in your coordinate system. It's a displacement from the equilibrium, which is important. So this is the case when the equilibrium is at 0. If you had it somewhere else, it'd be 1/2 kx minus whatever the equilibrium position is squared. So this is an example of an energy because of the configuration that something has, or the position that it has in your coordinate system. For the case of velocity, you have the same idea. In this case, you have the potential for a velocity, the kinetic energy, is 1/2 v squared. And the thing that couples to that is the mass, and so you get 1/2 mv squared. So the potential is 1/2 v squared, and the potential, or the potential in velocity space is 1/2 v squared. The energy in velocity space is 1/2 mv squared, and we call it the kinetic energy. Okay, so we have potential energy and kinetic energy. We know from the symmetry of the fact that we have a coordinate system where time is invariant under translations. The physics doesn't change if you change the time coordinate. That could be different if you had a clock, for example, that was running slower as time went on, or running faster as time went on, then energy would not be conserved. But if you have a clock where the clock ticks uniformly forward and it doesn't change, the size of the second doesn't change, then energy is going to be conserved. There's going to be a quantity called energy that's going to be conserved. And how that energy is shared is, you have like a total energy, which is the sum of the kinetic energy plus the potential energy. And it can slosh back and forth between these two things, but the total amount is always going to be the same. So this is going to be a constant in a closed system. Okay, so you have all these things that are interacting with each other. One of the things that, so I was going to mention, when you have a force, let's say, for example, here's a surface, and here is a block on that surface, and that block, it's rough. It's a regular surface, and you're pulling on this or you're pushing on this, either way, and so you're adding kinetic energy to the system by accelerating it in some direction. It's going to interact with the ground. It's going to bump into the ground. It's going to cause this thing to start shaking. It's going to emit some sound. As it drags across the ground and you start shaking the material in there, you're actually causing you're basically imparting kinetic energy to the individual particles that make up this block. So if you zoom in here with a magnifying glass or something like that, you have atoms, and those atoms are going to start shaking. This is my artist rendition of atoms shaking. They're going to start shaking more violently. Shaking is kinetic energy. And so the individual atoms in here are going to have kinetic energy that's random kinetic energy. And we have a name for it. We call this thermal energy. Thermal, that's an H, by the way, thermal energy. And so as we drag something across the ground, if there's some mechanism to transfer energy into the random motion of the stuff inside, we call that thermal energy. And in this case, the process of taking some of the total conserved energy, so energy is going to be conserved because it has to be, except now as we move something, as maybe it falls, maybe we're talking about something that's falling or sliding down a hill or something like that, and so it's losing potential energy and gaining kinetic energy. It's also, a portion of that kinetic energy is this thermal energy, and so it looks like energy is not conserved. It looks like somehow the energy gets removed from the system. In fact, what it is if you just have a standard setup where it's the kinetic energy and the potential energy, and you don't count this part of the kinetic energy, you don't count this thermal energy, which includes the energy dissipated by the sound waves as they propagate outwards, then it will look like energy is leaving the system, when the fact of the matter is energy is always conserved in this type of system, like in a classical system. We're not talking about a black hole. So in these systems, energy is always conserved. It's just that if our equation initially doesn't recognize some of the forms of energy, then it will look like that energy dissipates. So the conversion of regular kinetic energy or potential energy into thermal energy is a dissipative or non-conservative force. It doesn't conserve energy, but it only doesn't conserve energy because we're not talking about the kind of energy that is conserved. So that is what friction is. And in general, what is the rate at which stuff gets lost through this mechanism? If you're only considering bulk kinetic energy and potential energy, and you're not considering the thermal energy, what is the rate that energy gets dissipated or lost in the system? Is proportional to the velocity. So you'll have a force that is like minus something times the velocity. So this would be like air resistance. This is a dissipative force. So velocity dependent forces, it's not a fundamental dependence on velocity. It's just this is the rate that stuff is lost. So this would account for friction across a surface. It counts for air resistance. As something's falling through the air, you're going to reach a terminal velocity as the energy that gets lost from the kinetic energy or from the potential energy gets deposited into the thermal energy of the atmosphere, for example. So that is friction and dissipative forces, is transferring bulk kinetic and potential energy into thermal energy, which at this point, the book isn't really, the books typically aren't talking about this. Nevertheless, that's what's going on. Okay, so that is some of the stuff that I missed from last time. The next topic that I want to bring out is considering a little bit more this idea of you have potential energy and kinetic energy. So the total energy is potential plus kinetic. And this sum is going to stay the same. However, one might want to keep track of, for example, and I probably should have written this the other way, so let me do it. Let me go back and say that it's actually kinetic energy plus potential energy. That's the total energy. It's always going to be the same, at least in the systems that we're talking about, because we've chosen our coordinate systems and our time coordinate such that this is a conserved quantity. All right, remember, this is the potential energy is the energy that you get from your position, and the kinetic energy is the energy that you get because of your motion. The potential energy, because it's our coordinate system that we get to choose, you can always choose a potential energy so that you have a single object that is moving through, you have some single object at a given location with a given velocity. So here's your object at some location with some velocity like this. You can choose a coordinate system such that it has no potential energy and no kinetic energy. So you can choose a coordinate system attached to your object such that, so here it is right here, such that there's no potential energy. You basically assign this as 0 potential energy, and it has no kinetic energy because you're moving your reference frame along with the object. So to some extent, energy it's reference frame dependent, depends upon how you choose it. So what is important instead is how these things change as you move in your coordinate system. So let me go back and erase this and say, all right, now I've chosen a coordinate system and I have potential energy that might have some shape. This is the traditional shape that I'm using. And I have kinetic energy. The kinetic energy, this is an energy that's related to the velocity. And so in velocity space, so this is position space here, and this is the potential V in position space. I'm going to have to capitalize it to keep it distinct from this one, which is in velocity space. The kinetic energy, we know what the potential looks like in kinetic energy, which is a parabola. Looks like this. Okay, so this is 1/2 v squared, and that's velocity squared as opposed to potential here. So we've got 2 v's, which is kind of going to suck, but we've already started. Maybe I should switch this right now as long as I have the opportunity. So I'm going to call this u instead of v. Call this potential u instead of v. All right. So if you're moving with some speed, then you have kinetic energy that lands on this spot. Your total kinetic energy is going to be your coupling here, m, times the value of the potential, which is 1/2 v squared. So 1/2 mv squared is the energy that you have if you're displaced from 0 relative to your coordinate system by some amount v in velocity space. Similarly, in the potential energy space here that depends upon x, your energy is going to be here. It's going to be u times x is the total energy that you have. It's where u is the coupling, the charge that you have times the potential at the location times the value of the location in this case. Okay, so this whole thing is conserved, but what we may wonder about is how is the energy sloshing around? Because these two things are degenerate, right? Kinetic and potential energy, they all have units of energy. Energy can be transformed between one and the other. And so the sum here is going to be the same, but we may wonder how is this stuff being distributed between these two? Which one has more and which one has less? In which case we could rewrite this. We could come up with a different expression that tells us more about whether the potential energy, there's more potential energy or more kinetic energy. So in that case, let's put up another quantity. In this, it's called the Lagrangian, but that's giving away something. So I'm going to come up with another quantity. I'm just going to do it L because then I don't have to worry about it. So here's another quantity, and in this case, it's going to be the difference between the kinetic energy and the potential energy. Now, why would we care about something like this? Well, if you have, in this case, if the potential energy, your object has more potential energy than kinetic energy, then L will be less than 1. If your object has more kinetic energy than potential energy, then your object, then this L will be greater than 1. So you have the sum here and the difference here. That basically, if you look in the space of potential energy and kinetic energy, the fact that energy is conserved lives on this line. The sum is going to be equal to some value, right? The sum of x plus y is some number. looks like this. That's a line that looks like this, has a negative slope. In this case, the difference is this line right there that goes this way. And it tells you basically which one of these is bigger. If you have more potential energy than kinetic energy, then you'll be negative. Let's see, did I do this the right direction? It's got to be. So this is right. It's got to be right. Kinetic energy minus potential energy. All right, so it's going to be like this. Okay, I got to draw this. That's the slope 1, intercept down here at negative this. So it's going to be like that. So if you have more potential energy, then wait a minute, what's going on here? Why is this having why? Oh, because potential energy. Okay, hold on. I got it. So this gives me what? Potential energy equals kinetic energy minus L. So this is L down here. Anyways, the point being that if the potential energy is bigger than the kinetic energy, you're going to get a negative number. And if the kinetic energy is, what did I do wrong here? I can't believe this. It's like basic algebra, and it's not working the way that I expected it to. Potential energy that's potential energy is a function of kinetic energy minus L. Looks like that. What is it a function of T? So I'll get to that in a minute. Anyways, the point being, so ignore all this stuff. It's not as important as I thought it would be easy, and because it didn't. Well, it is easy. It's just I'm doing it on the fly. So the point being, in all of this stuff, this wonderful exploration, is that if this is negative, if L is negative, that implies that the potential energy is negative, because kinetic energy is always positive. If L is positive, then that implies that the kinetic energy is always positive, or that you have negative potential energy. So this quantity here, this difference, tells you how the energy is split up between kinetic and potential energy. The total energy here is going to be some number, and it's going to be conserved. This quantity here is not a conserved quantity. It just tells you whether you have more of one type or another type. All right, now these things, this quantity here, it depends upon what? It depends upon these different forms of energy, the potential energy and the kinetic energy. And as the energy moves around from one type to another, the value of this function is going to change. Okay, why would we care about some mathematical construct, right? This is a social construct. It's named, it's given L because it's named after a guy by the name of the barn, Lagrange. And it's the Lagrangian. So Lagrange means the barn in French because of Monsieur Lagrange, who figured this out, or at least who it's named after. Okay, let's take a look at this Lagrangian. And so this is the potential energy minus the kinetic energy. I did it wrong again. It's the kinetic energy minus the potential energy. So that's what this is equal to. All right, let's take a look at what's going to happen. So we have the kinetic energy over here that looks like this, and we have the potential energy over here that looks like this. And here is where we're located at some position. Okay, what's going to happen if we move our object in space in some direction? We move our object like this, so it's displaced a little bit in the x direction. It's going to climb in potential energy. The potential energy of this object is going to go up. The amount that it's going to go up is equal to the slope that you have at this location. So here's the slope, and you displace it some small amount, and it's going to go up by a small amount right here. It's going to go up by this. Well, the slope of this line at any given point is the derivative of the line at that point. So the slope is, again, this is, we'll call it u, because I'm going to need v for something else. So I'm going to call this u. So the slope is the change in u with respect to x, right? Because that's what slope means. And the distance that you're moving is a little bit dx like this. So this is going to be the change in the potential energy is equal to the slope times the amount that you displace. So this is like the change in potential energy, like that. Okay, what does this mean? Well, the change in the potential energy, this is going to be, if you look at the Lagrangian, at this quantity, it's got a minus sign associated with it. So the Lagrangian minus the change in the Lagrangian from this small displacement in x. So we take our object and we displace it in the field. We displace it in whatever field it's interacting with. And it's going to be interacting with all the fields, but in this case, it's whatever field we happen to be caring about. All right, so the change in the Lagrangian with respect to that displacement is going to be equal to minus the change in the potential with respect to that displacement. So that's going to be minus du dx times dx. So this is the slope. This is the slope right here, and that is the displacement. Or in other words, I can just put this minus sign over here. Which one do I want to do? I don't remember which one I want to do, so we'll come back to it and see which one I actually want to do. Where we put this minus sign will be important later, but it's not really that important now. I'm pretty sure this is the way that I want to have it. Okay, so that's something that's interesting to think. If I displace this object in these fields, then it's going to cause a change in the potential energy by this amount, and that corresponds to a change in the Lagrangian by minus that amount because it comes in with a minus sign right here. All right, now, when you change the potential energy, so I've displaced this thing in my ambient field, that energy has to come from somewhere. And if energy is conserved, then it's going to have to come from the kinetic energy. And the kinetic energy here, this is velocity in this direction, and this is the kinetic energy. So if I increase the energy in one direction, because energy is conserved, I have to decrease energy in the opposite direction. So this is going to cause the velocity to get smaller. So that means that the change in the kinetic energy, so like dt, is going to be equal to whatever the slope is here, which happens to be, it's v, right? Is that right? Is that what the slope is? So the slope is the tangent right here. Anyways, it's dt dv times dv. Okay, so the amount that the kinetic energy changes, we'll change this again. The change in the kinetic energy is, okay, so a bit of background. T is a standard notation for kinetic energy. That's what when I took mechanics in undergraduate, we called it T. Anyway, so change in the kinetic energy. Now that I've said that, we'll use T. Change in the kinetic energy times dV. That's how much this kinetic energy is going to change. And in this case, the change in velocity is going to be negative, but that will come out when you actually calculate which direction you're moving. So if you displace the potential energy, that's going to cause a change in the kinetic energy because they have to be connected to each other. And those two things have to be equal to each other. So let me go back a little bit. Lagrangian is equal to, in this case, T minus U, or T minus capital V, or whatever letter that happens to be. And what I've mentioned is that a change in potential energy is going to be minus, a change in potential energy is going to be dl dx is going to be, in this case, minus du dx times dx. So this is the slope. This right here is the slope of potential, of the, whatever the potential energy happens to be. Here, that change in the slope on one side is going to cause a change in the kinetic energy. That change in the kinetic energy is going to be dt dv times dv. So it's whatever the slope of the kinetic energy function is times dv. And that is going to be equal to something also related to the Lagrangian. That's going to be what? dl dv. So these two things have to be related to each other because the total energy is conserved. And so when you change one, you have to change the other. And so somehow there's going to be a relationship that connects this thing, this term here. The change in the potential energy is going to be related to this change in what turns out to be the kinetic energy right there. And what it really boils down to is matching the denominators. There's some subtleties here that I'm glossing over, but you match the denominators. In this case, dv, so somehow this derivative here is related to this derivative here. The change in the kinetic energy and the change in potential energy have to be related to each other. So what does that boil down to? when you work out the details, you end up with the following relationship. So let me get this down. We'll write this down again. L equals kinetic energy minus potential energy. And the relationship you come up with is that the time derivative of the Lagrangian with respect to velocity is going to be equal to the time derivative. Time derivative of this with respect to velocity is going to be equal to the derivative of that with respect to position. So this is the fundamental relationship. So again, let's take a look at what this actually means. What this means is, in this case, this is minus the change in potential energy with respect to position. Okay, and this side over here is going to be the time derivative of the change in the kinetic energy with respect to velocity. So that's what this relationship implies. All right, now let's think about this. Here is my two potentials. Like, this is the potential for kinetic energy. It's just 1/2 mv squared, so it's got this parabola shaped thing. And then this is my potential energy here, which only depends upon position, or that in this case depends upon position. So I have some velocity. And what I said before is that when you have something like this, it's going to be, if you move up in, if you gain some potential energy somehow, you add potential energy to your system like this, it will slow down the velocity. In the absence of some external force, the velocity is going to slow down. But what's happening here is nature's going to resist that. It's going to exert a force that is in the opposite direction, and the strength of that force is proportional to the slope here. The steeper the slope, the harder it is to push it up, the stronger the force is going to be pushing it back. So we experience a force as the action or the consequence of a gradient in the potential energy. So here's the potential energy. You have an object that's coupled to that field. It's going to be pushed backwards against, or like away from the slope in that line, or the slope in the potential energy function. So that means this right here, this is the force. Okay. If we look over on this side, this says that a force, which is the opposite of the slope, it's pointed in the opposite direction, and it's proportional to the slope of the energy that you get from the configuration, is going to cause a change in the kinetic energy. Well, what does kinetic energy look like? Kinetic energy looks like 1/2 mv squared. This is a 2, by the way. 1/2 mv squared. And if I take the derivative of that with respect to speed, so now I'm saying, okay, this force is going to cause, it's going to drive something in a different direction. As this goes down, conservation of energy says that this is going to have to go up, like that. And the change in kinetic energy with respect to velocity, because this is the kinetic energy side, and it's squiggles v squared. So I take the derivative of this, what's the slope of this thing with respect to v, and I get mv. So this change, kinetic energy, the slope of the kinetic energy function is this quantity right here, mv. So that says a force causes a time derivative with respect to mv. This is momentum. So what does this mean? This says that forces cause a change in momentum. So F equals ma. Forces cause a change in momentum. That's Newton's second law. Newton's second law comes from conservation of energy and the fact that things are related to each other. Energy and moment, or the two different kinds of energies, are related to each other through this relationship. That you have a total amount of energy that's got to be conserved, and this quantity here, this Lagrangian, is a way of storing that information that tells you which one, where the information is located, or where the energy is located. If the energy is located primarily in the potential, it's over here. If it's located in primarily in the kinetic energy, it's over here. And as the energy sloshes around back and forth between these two things, the result of that, or the consequence of that, is Newton's second law. So it falls directly from the fact that this is how particles interact with each other. You have conservation laws associated with your reference frame, and you have different fields that produce a potential that give you energy depending upon the position that something has, energy that depends upon the position that something has. And you have this mathematical construct that tells you what the kinetic energy is associated with something based upon the velocity that it has. And your reference frame is a function of some initial velocity and some initial position. So you choose your reference frame that gives you a potential energy and a kinetic energy associated with that reference frame. And the relationship between those two energies gives you Newton's second law, how energy gets transformed from one place to another, or how you affect change in one place or another. So that's kind of an interesting thing. And this is weird because, for a variety of reasons. One is these potentials can be based upon other things, and these kinetic energies can be based upon other things. For example, you can assign a kinetic energy of rotation. So here's your object that's spinning around. And you can say, I don't care necessarily about the instantaneous actual physical velocity through space that a given chunk has. Instead, I'm going to give a velocity. In this case, it would be, it's given by omega, which is the speed that something is rotating. So instead of having this be a velocity as in the velocity in the x direction or the y direction or the z direction, I'm just going to have a general velocity that is how fast is this thing rotating per second, how many radians per second or degrees per second is this thing rotating around. And so I have a generalized velocity, and I can have a kinetic energy that depends upon this velocity instead of the instantaneous velocity of microscopic chunks of it moving in some direction. And I get exactly the same results. So the difference is here, so now I have a Lagrangian. My Lagrangian is going to be, the kinetic energy plus the potential energy. And what I end up with is a relationship that is not F equals ma, but rather a torque is equal to some substitute for the mass. In that case, it's called the moment of inertia. So it's this mass quantity times the acceleration, which is going to be the time change in this velocity. So the time change in that velocity is given by omega dot or alpha. So in this case, when you have these energies and you formulate something with a Lagrangian, you don't even have to use spatial coordinates, x, y, and z coordinates to do it, to come up with the right physical laws. Instead, what you come up with is what is the description of energy that associated with motion in a particular direction? What do I going to call a velocity that is associated with motion in that direction? So in this case, the velocity is this angular frequency. I'm going to have a mass associated with that kind of motion. In that case, it's going to be the moment of inertia, which is moment of inertia is like mr squared, basically. You add it up across the surface. R is the distance from your rotation location, like where the thing is fastened, that you're rotating around. But you're formulating a new kinetic energy, which is I omega squared, 1/2 I omega squared. So this is the kinetic energy that's associated with rotation. And you don't even have to, so now you can formulate your, the motion that something is going to have using the Lagrangian that doesn't use x, y, and z coordinates at all. It's just angles. So for example, you could imagine this wheel, if you have this spinning wheel. So here is a cross section of the spinning wheel, and it's attached to a spring. So as it spins up, the spring is going to have, it's going to get distorted and store energy in it. So you're going to have a potential energy associated with that distortion, that torsion spring. It's a torsional spring instead of a linear spring. So as this thing spins, you're going to build up some potential energy, and you can come up with a formulation for what that potential energy is. In this case, the potential energy is going to be some spring constant, some rotational spring constant, K, and it's going to be K times the angle that you've rotated through. The more you've rotated through the angle, the stronger this becomes. And it's going to be 1/2 K times that thing squared, because that's the nature of things. It has to do with like, well, this is what it turns out to be. It comes down to, fundamentally, it's the electromagnetic interaction of all the particles in that spring. But this is a different formulation now using rotational coordinates, like a generalized coordinate instead of a position x, y, and z. It's a displacement in rotation from equilibrium, theta, and your velocity is the speed that you're moving in that particular direction, omega. And Lagrangian formulation gives you this law right here. So we haven't even, like this is, I guess, 2 chapters from now. But this Lagrangian formulation where you have kinetic energy and potential energy minus potential energy, and you have that equation that relates these two things, the derivatives of the Lagrangian with respect to all this, is a way to solve what's happening, to come up with how do these things, how does the potential energy and the kinetic energy relate to each other? How do you transform kinetic energy into potential energy and vice versa? And that is given by this, F equals ma, or in the case of the rotation, torque equals the moment of inertia times the acceleration. So Newton's second law is a way of translating from one type of energy to another. What that tells you is that forces cause energy to transform from potential energy into kinetic energy. So there we go. So here's a question. Could you get enough hydrogen from water to power a car? Yes. There's plenty of, the question is, do you get enough energy from hydrogen in the water? Does the cost, the energy cost that it takes to extract the hydrogen from the water provide enough more energy than, is the energy you get for your car more or less than the energy that it takes to provide the hydrogen in the first place? In that case, the answer right now is no. Okay, let's see. Oh, so one last thing that I wanted to point out, and this is related to something that came up in the questions last time, and that is we have this Lagrangian like this. It's got this potential energy, or the kinetic energy minus the potential energy. And someone had mentioned, you know, what about if you have a charged particle moving in an electric field or a magnetic field? And so there's this force law that is given by force equals Q times E minus E plus V cross B. It looks like this. So this is a charged particle moving in a combination of electric and a magnetic field. So you have an electric field and a magnetic field. Charged particles are going to be distorted, like their path is going to curve because of the presence of the magnetic field. And this is the kicker. This is what someone had brought up, is what do you do with this velocity right here? So what the book generally tells you is if you have a velocity dependent force, so what textbooks generally say is if you have a velocity dependent force, it's typically going to be a friction. So you're going to have like friction as a block moves across the ground, it's going to add thermal energy, and the rate that it adds thermal energy is proportional to the velocity, which means it's pulling stuff out of the system, pulling energy out of the bulk motion and putting it into the random motion. You could have air resistance, so you have a block that's falling. So here's it falling down through air and is depositing energy into the air, and as a consequence, it loses energy from its kinetic energy. So those are both velocity-dependent forces, and so the book says, well, velocity-dependent forces don't conserve energy. Well, they do conserve energy, but the energy is, you have to count for the thermal energy. You have to count for the random energy of either the air or the block in the system. In this case, with this electromagnetic force, when you have a charged particle moving with some velocity in an electromagnetic field, it's going to be, it's going to feel a force exerted on it. It's going to just change the velocity. It's going to cause some kind of acceleration. So what's going on here? If you go back to this formulation where we had with this Lagrangian, where you have d dt of the Lagrangian with respect to velocity is going to be equal to, that's an equal sign, equal to the change in the Lagrangian with respect to position. Do I have that right, or do I have, I think it's, I think that's right. Yeah. So as long as, if you can come up with a potential, if you can have a potential that maybe the potential actually does depend upon the velocity. So if you can describe or formulate a potential that depends on both position and velocity, however, that its dependence on velocity is exactly of a form that looks like this, so it satisfies this mathematical structure, then basically what happens is you have a potential energy that depends upon both position and velocity. And what you can do is separate the velocity term out and move the velocity term and treat it as though it's a kinetic energy. Okay, and that's what allows you to have electromagnetism, where you conserve energy, but it's still a velocity dependent force, is that this form of the potential that you can describe that depends upon velocity has exactly the form that you need to take the velocity dependent portion of the potential and treat it as though it's a kinetic energy. Is basically, so that was in response to a question that came up last time. Okay. So that's Lagrangian mechanics in some, I don't know, it's the first time I've tried to explain it in this method. So there we go. Let's take a look at what is next in this material. So we talked about drag forces already. That's this stuff right here. We talked about Newton's laws and how Newton's laws are basically, well, it turns out Newton's laws are how you, map, how you couple forces to your mathematical model. So your mathematical model is basically the kinematics. How do you describe the motion of something? How do you describe the interactions? They come in through the forces. Turns out that those forces are a way of transferring energy from one type to another. So all the forces of nature, photons, like the electromagnetic force, the strong nuclear force, all of those things are a mechanism to transfer energy from the potential energy to the kinetic energy, or vice versa. Okay, and that basically gives you Newton's laws in the end. And so we talked about how energy is conserved. We have non-conservative forces, which are ones that depend upon velocity, unless the velocity has a very specific mathematical description or satisfies a specific mathematical relation. And that was that you can express it in this form. Where is it? You can express it in this form right here, in which case then it's not just velocity dependent forces. In which case there are some velocity dependent forces that still would be considered conservative. They don't transfer the energy into thermal motion. Okay, and so momentum right here. This is the next step in this progression. So we've talked about that momentum is a quantity of motion, that forces cause change in momentum. What we haven't yet mentioned is the fact that momentum is conserved, or maybe we did and I forgot. So I just talked about before how if you have a coordinate system, so if you choose a coordinate system where all of these things are equally spaced, then there's a conserved quantity associated with that direction. So if it turns out that your coordinate system is not equally spaced, then you would say there's something that's not conserved. Something is changing. If I have an object that's moving to an outside observer might be a constant speed, but in my coordinate system, the speed in this case would be speeding up. Then there's something that's not conserved associated with it. In this case, what that is momentum. So momentum is a conserved quantity provided that your coordinate system is uniform in the direction that you're considering. So you can have a coordinate system, for example, where it's uniform in two of the directions. So you have a uniform reference frame or uniform coordinate system in these two directions, and a non-uniform coordinate system in this other direction where your tick marks are differently spaced. And so momentum would be conserved in this direction, it would be conserved in this direction, but not in this direction. So if it's not conserved in this direction, then it would look like, you would interpret it as though there's some force acting on it that's causing a change in momentum in that direction. So the gravitational field, the way that Einstein formulated it, is exactly this, that there's the coordinate system coming out from a massive object is not uniform. The spacing is not uniform. And as a consequence, it looks like an object is actually accelerating when in fact it's just moving freely in a coordinate system that is non-uniform in the spacing. However, in general, the way that we look at something, when we analyze something, especially in high school AP physics, is we say, well, all coordinate systems are going to be uniform in all directions, and so momentum is going to be conserved in all directions. And if we see something that violates conservation of momentum, that would imply the existence of a force. So forces cause changes in momentum. Force equals dp, p is momentum, dt. Okay. Let's see. So what this implies is that momentum can be shared. You can, when two objects collide or hit each other, then they're going to exchange some information with each other. So you have two objects that come in, they bounce off of each other, they're going to move off in different directions. And because the momentum that they have coming in the total momentum they have coming in has to equal the total momentum they have going out. just like the total energy that they have coming in has to equal the total energy that goes out. A difference between energy and momentum is that energy always, there's a variety of different forms of energy that you can have that depends upon the ambient fields, like gravitational field or electromagnetic field or whatever. So there's a variety of different energies that an object can have, but fundamentally there's only one form of momentum that an object can have, and that's momentum in a particular direction. So objects come in, or objects are going to have momentum in all directions, in all spatial directions. Each of those momentum is independently conserved because there's no momentum potential. I wonder, it's possible, I guess, to think of the kinetic energy in that form. I'll have to think about that one. So anyways, momentum is conserved, and as a consequence, you get, when you define a closed system and the particles interact with each other, you can use the fact that this is constant. If there's no external forces acting on the system, then whatever momentum the objects have in the system to begin with has to equal the total momentum they have in the system to end with. They can share it between themselves, and the way that they share it is they come close together. Here's one object like this. Here's another object like this. The electrons in one object interact with the electrons in a different object. Those electrons will communicate with each other through exchange of photons, and then they bounce off of each other. And all along the way, the total momentum of the system is conserved. Just like all along the way, the total energy of the system is conserved. All right, so that's basically momentum.